So
Go ahead, please.
I work in EDF. So EDF is the main French electric utility company. And today I will speak about Verrou with a panorama of the localization method. So it will be mainly a user point of view, but I want to hide nothing about the internals. So if you have questions about it and if you want more details, I will be open. I will be. It would be a pleasure to discuss about that. I need to give a little bit of context in EDF in order to explain why we want to be able to work with floating point. Yeah, we are doing a lot of simulation in EDF to guarantee the safety, to improve performance and cost of because we have a lot of nuclear power plants, of turbine, of wind turbine, of dams, and we need to be able to do simulation of the physics of these tools. And we have also an issue with edging, and so for that the authority forced us to do a lot of numerical simulation. And to do that, we developed a large number of in-house code. There, I see only the free software, so it's quite famous. So there is Codaster for thermomechanics, there is Code Saturn for computational fluid dynamics, there is OpenTeleMac for free surface flow, and there is also Salome, which is a simulation platform. But we have also a large number of closed source software. It's not possible to share everything. And all these code have common properties. The first one is a huge code base. By example, Codaster is it's more than, I think, 2 million lines of code. There is various languages, C, mainly C, C++, Fortran, Python. We use external libraries, so by example mumps or numpy, and we have an important and a good VNV process, so verification and validation. And almost all these tools follow the same scheme. So we begin by a physical phenomena, and then we have to introduce a mathematical model, then a numerical algorithm. We have to implement it, and at the end, on a computer, you are able to get the computed solution. And at each step, you introduce error, so modelization error, discretization error, bug, like memory bug, and at the end, there is a floating point error. And in the VNV process, we have to be able to measure, to do the estimation of each kind of error. And today I will speak about the last one, so the floating point error. And for this error, we need to develop a tool which is compatible with our code properties, and there is not a lot of solution to deal with it. And so we developed Verrou, and there is the two main ingredients of Verrou is the binary instrumentation based on Valgrind. So we are able to run the analysis of almost every binary. And the second point is the asynchronous stochastic arithmetic, and I will detail this arithmetic a little bit later. And the two main functionalities are the error estimation and error localization. So first, I have to explain shortly what is floating point error. And in fact, it's the error implied by the floating point representation with a limited precision. In our code, we use float representation or double representation, which is 32 and 64 bit, and it corresponds to 24 significant bits and 53 significant bits. And for the physician, it means that there is, for each operation, there is a relative precision of 10 to the power minus 7 or 10 to the power minus 16. So it's really small, but the problem comes from the propagation. So in my slide, it's not possible to explain everything with binary. So I will use decimal and only three significant digits. And the problem of the floating point representation is you can take two floating point numbers, 1 and 3, and if you do an operation like 1 divided by 3, the result is not necessary a floating point number. So you have to round it. Usually you round to the nearest. So in this case, it's the downward. But by doing this, the floating point computation is not the same than real computation. So it's what is written with the first formula. The plus in floating point world is not the same than the plus in mathematical world. Another problem come with this is the loss of associativity loss, and the way we put the parentheses in an expression. It's true in the way for real computation, and it become wrong, and we are able to see that easily when we change because it's the main source of loss of reproducibility. When you modify your compiler option, when you change of compiler, when you change your architecture, when you introduce parallelism, you play with the parentheses. And so you are able to see that you have different results. And the problem is not necessarily the fact that we have different results. The problem is it's a good way to see that the result can be wrong. And that's why we really need tools to be able to do error estimation. So for that, we use stochastic arithmetic. And the idea is really simple. Instead of rounding to the nearest, we introduce randomness, and we have a probability 1/2 to round downward or to round upward. We are doing that for each floating point operation in our program. So it's like a Galton board. When I see one floating point operation, I can go left or right. And at the end of my program, I can extract the value of interest of my program, and I can get a distribution of result. Because I run my program several times with this random rounding. So I can give a small example with a really easy program, 1 divided by 3 and this result is multiplied by 3. So I'm expecting 1 in the real world, and with the evaluation with round to the nearest, I will get 0.999. And so to perform stochastic arithmetic, I can run several times, 3 times there, my program with random rounding. And one thing you have to I don't know if you see my pointer, but there there is no rounding for the second operation of the first evaluation, because the operation is exact. And when it's exact, we do not introduce more noise. It's really important at this point. So we run 3 times with stochastic arithmetic. We extract all the 4 value, and we can use the 2 formula above to compute the number of significant bit or digit. And it's mainly based on the distance of each sample to the result to the nearest. And after, if you want a number of significant or digit or bit, you select the good logarithmic base. So on this small example, we have almost 2 significant digits. Yes. So this method is really nice because it's easily compatible with binary instrumentation. And so it's what we have done with Verrou based on Valgrind, but it can also be done with low-level LLVM path for the compiler in a tool called Verificarlo. It's very similar. What is nice is we need to modify only the result of floating point operation. We don't need to use extra memory. We don't need to modify the memory layout. And so the result is we are able to do really robust instrumentation. And so we are able to make it work with industrial program. And the other point is there is few false positive detection compared to the synchronous stochastic arithmetic. And we have developed the last 2 years. We have developed new stochastic rounding. It's a little bit more complicated, difficult than probability 1/2 to go up or to go down, but there is no more false positive. So yeah, I won't spend too much time on it today, but now I don't know so much false positive. So for in an industrial context, this point is really, really important. So for the demonstration, I will use a really, really easy program. It's the rectangle method. I want to integrate one function between one function f between 2 bonds A and B, and I use the method of rectangle. So it's just a summation of the summation of n terms, which correspond to the area of a small rectangle. So I can write this small program. So what to say? See, I compute the step between the distance between each point of integration. I perform an initialization, 0 for the sum. Then I compute in the for loop the first point, and I increase the number x by the steps, and I stop when I reach the last bound. So it's a really bad way to write this loop, but I need a bad program to illustrate how to solve it. And then we just have to add the small rectangle to the main contribution. So now we have written our function for the rectangle method. We need to do verification, and what we can do is we will do a convergence analysis with a function where we know the result. So we can use the integration of the cosinus between 0 and p divided by 2. We know the result, it's 1. And so and so we increase the number of rectangle. We compute for each number of rectangle the result of our function. We are able to compute the error, and we plot the result for each point. Yes, and so with that, we can get this result. So there is a text form, and with more point, I'm able to plot. I'm able to plot the error, and what we see is at the beginning, with less than 200 rectangle, we have the expected convergence, and after, at the end, the error is go up, and so it's not what we want. And if we and now we can think that it comes from floating point, and so we will use Verrou to prove that. So first, I will begin with the manual analysis.
I apologize for the interruption. If we go back a slide, I'm afraid your explanation of this plot went by fast enough, and I notice it gets used a lot later on the talk. I really hope maybe you could just go over this plot one more time to make sure I get it for later slides.
Yes, yeah, you are completely right. So
thank you very much.
Are you able to see my pointer?
Yes, just fine.
Perfect. So on this part, there is a number of rectangle. So when there is too few rectangle, you are expecting a bad error, because if there is only one point to do the cosinus approximation, your integral will be bad.
So let me just double check. In your formula, NB rectangle is just n, right? The number of divisions between A and B, the number of steps.
Okay, exactly.
Perfect. Okay, this plot makes a lot more sense now. Thank you very much.
Perfect. So it's just this plot is interesting because it's a way to see that there is relationship between the floating point error and the discretization error, and it's something we are in real industrial code we can see quite easily. So now I can run my to do the manual analysis. I can run my program and to store the result in this file, in the first file, to store the results. I can run the same program just by using Verrou with a prefix command. So it's really easy to do. So I specify there to use Verrou. I specify there with rounding mode equal random to modify each floating point operation by random rounding. And the last part is just to say we use the mathematical library with the cosinus, and so we need we may want to instrument it. And so there by this part we instrument this the mathematical library. And we store the result in a new file. And the next step is really easy. You use simply a graphical diff command, and you will see the difference. And where it's red, it means that you have problem. Just one thing, you have to take care about the change when you change of decade. When there you are close to 1, and there you are also close to 1, but everything is in red. So just because we change of decade. So it means that it's still useful to use a proper error estimator, but yeah, to just have an idea when you have a full program to see where there is problem, it's still a good idea to use graphical diff. And yeah, and when you want to understand when how Verrou works, it's a good idea. So there you can see that you have problem just with one sample. You don't need every time a lot of sample to see if there is problem. So now we can do it properly with 20 samples, and you can plot the error estimation on the and compare to the error of our method. And what we can see is you can explain all the error of our method by floating point error. So yeah, and it's really nice because I'm able to do that without knowing the mathematical reference. So there, it's a toy program where I have the mathematical reference, but I'm able with Verrou to do this error estimation without the reference, and I'm able to explain the difference when I'm able to get the mathematical results.
So I apologize for interrupting. Just a very quick question again. The crosses, the mathematical reference, that also came from Verrou, right?
No, the mathematical reference is it's the last column of my program.
Okay.
Because I'm able to compute the error.
Oh, I see. Okay, perfect. Thanks.
Yeah, and this one come from the second column. It just comes from the result.
Yeah, perfect.
Is that clear for everybody?
It's definitely clear for me now. Thank you.
Because the next part will be difficult if if this part is not clear. So if there is other question, maybe it's a good time to do it. So I can continue. So now we are able to compute the error coming from floating point, and this approach works with every industrial code. It's really easy to use. I think it's really important to know it. And but if I only able to say to my colleagues that their code are wrong, it will be difficult for me. So I need to be able to help them to localize in their program where the problem happened. And to do that, we can use a kind of trial and error search algorithm. And the idea is, with Verrou, we are able to select the symbol or the line of code we want to perturb. We can say, I want to modify, to introduce random running only for these 2 lines, only for half lines of my program. And so by kind of dissection, like a git bisect, I'm able to localize where I have problem. So for the user, it means that the user of the Delta debug need to give 2 programs, 2 small scripts. The first one is to how to run your program with Verrou. So you can see there there is your program there. There is the valgrind command, and one important thing, you have to store the result of your program in a specified work directory. And this directory is controlled by Verrou DD line. So you store your results there, and after you have to give a second script to do the comparison between one reference and the current configuration, so the current set of line. And to do this comparison, first you have to extract the value of interest. So you can open the file where you store the results. So rest on that, and then you can do you select the value of interest. There I select the last line, so it means the method of rectangle with 100,000 rectangle, and I select the second column, so only the value of interest. I ignore the error. So I extract this value, and now so the first if statement you can ignore it. Just a good way to write it for another application. So, but for the delta debug, you just need the last case. So you can read the reference value. So it's the first directory. You can read the current value, and then you compute a relative distance between both. And if you are, and you as a user, you need to define a threshold. And if the distance is acceptable for your needs, you return a success. And if you have problem with that, you return a failure. And from that, you just have to run these commands, and you will get the two set of lines where you have problem. And the first set of lines, there is only one line, and it's line 17 in my program, and the second one, it's line 16. Yeah, one important thing you have to as is it's a stochastic approach, you have to specify the number of samples. Yeah, and if your script is parallel, I mean, if your script there is parallel, you can specify a number of threads if you want. Yeah, it's quite long, but at the end you have the right information where you have problem in your code. But what is the information you get is the origin of floating point error. It's only origin. I mean, if you are doing somewhere a small floating point error, and then this error is amplified, it will be the first. It won't be. You are not able to localize with this approach. You are not able to localize the amplification. And there is two ways to do to get amplification. Usually, it's cancellation, and as cancellation are exact operation, you are not able to detect it with delta debug. And the second one is unstable branch. By example, if I'm doing a floating point computation to compute a temperature, and then depending on the temperature, I select one physical method or another. And depending on the threshold, sometimes you have two completely different stories, and you have an unstable branch. And so you are not, with this approach, you are not able to pinpoint this much. Yeah, it's really useful. It's the method I use the most to help to localize problem in my codes. But there is this drawback, and we tried to solve this problem. And to do that, the idea is to use code coverage. I don't know if you are familiar with code coverage, but the idea is code coverage usually is used to know if you have enough tests in your test test case suite, and so you can get all your code with prefixed by the number of line execution. And now we can do that for only one test case, and we can do a comparison of the code coverage for nearest rounding mode and a one with random rounding mode. And when it's different, when there is difference, you know you have a problem with the if statement, and so with this comparison there, just because there is no the same number of call of this line. This method is really nice when your code is not too unstable, because if your code is really unstable, everything is red, and so it's impossible to analyze. So that's the first problem. The second problem is there is false positive. If there is a if statement, and if in the first block and in the else block you are doing exactly the same thing, this approach, you will see difference with this approach, and there is no problem in your code. So yeah, with this approach we've got big success in industrial code like Codaster, but sometimes it's too difficult to use. And the last problem is to reduce the false positive, you want to minimize the introduction of random noise, and the good way is not to apply randomness for all the program, but only for the result of the delta debug. And as you need to recompile your code for the coverage, you need to rerun delta debug, and sometimes it's quite long, and so you don't want to do that. And so we try to solve this problem, and we can do it. It's a little bit, and so the idea is to replace the code coverage by a basic block coverage. So a basic block, it is a sequence of instruction in my binary without branchment, and I represent it. I'm able to represent it with all the debug symbol in my basic block. And with Verrou, we are able to do this coverage, and we can apply, and we can use the result of delta debug. So for the first comparison, I'm able to introduce random only for the line 16, and I'm able to do the comparison with round to the nearest. And now it's a little bit more difficult to analyze, because from this line and from the name of CMAT, I'm able to see that there is no the same number of call to the cosinus. So it means that the loop, we do not loop the same number of time. It's a little bit more difficult to analyze, but I'm able to do that for the result of the delta debug. I'm able, so for the first one is for line 16, the second one is for line 17. And so I'm able to see when I modify only the line 17, there is no problem with coverage. And yeah, and to say that, I need to do the comparison for all the sample, all the sample of random. To say there is a problem, I need only one sample there, and there I need to do this comparison for all sample to be able to say that there is no problem with branchment with the line 17. And what is really nice compared to the code coverage is we can generate this automatically with a post-Verrou DD, just to say that it's a post-treatment of the delta debug. Now we can come back to the code to analyze what we have seen. So the first problem was with line 16, so with the increment of x, which produced a problem with the number of loops. And so the good way to improve it is to replace this loop with a float criteria with an integer loop. And like this, you are able to do exactly the good number of rectangle. And the second one, you know that there is no problem with the if statement there, and the only way there is two ways to solve it is to add precision to this accumulator. So you can replace this float type by higher precision. So if you are in float, you can use double, and if you are in double, you can use quad. And the second solution is to use compensated algorithm. Sometimes the basic block is quite difficult to analyze, and you want to be able to get a coverage only for one iteration. When you have kinetics, you are doing a kinetic simulation, or when you have in linear algebra, you have an iterative algorithm. You want to have only to get the coverage only for one iteration. And it's a good way to avoid the problem coming after for the next iteration, and it's easier to analyze. On top, there is the basic block coverage, and on the second one, it's a basic block coverage only for the last iteration, and it's easier to analyze because you can see that you can know what is your expectation, because you are doing you are computing the integral with 100,000 rectangle, and so you are able to see that there it's the wrong number. It's easy to analyze compared to the first one where you have to know that you have to analyze the previous problem before, so it's more difficult. To do that, there is two ways. The first one is to use client request like in Valgrind, but you need to recompile your code, so you understood that I don't like it. And so the second way is to provide an IO match script developed in Verrou. And the idea is it's a way to call client request by reading the standard output of my program. And when in the program you are able to match the specified line there, you are able to apply, Verrou will apply this client request. And so what I'm doing there, before the iteration and at the end of the iteration, I dump all the coverage, and so I can get the coverage for the last iteration. The next point is sometimes the delta debug for the line is not the good search space, and when you work with iterative algorithm, sometimes what you want is to know if the problem happened at the beginning of your iteration or at the end, and for that you want temporal delta debug. And the first easy way is to use Verrou DD task with a manual definition in your source of what is a task. It's quite easy, but as always, you need to modify your source code, and you want to avoid it. And you also I have to mention you can use this functionality with automatic way to define this task for a Python script, and it means you are able to have something equivalent to Verrou DD line for a Python script. So yeah, so this tool is really useful for a Python script. And the second way to get temporal delta debug is to use the standard output to define the task, and you are able to detect the task thanks IO match. And what is really nice is you have to modify nothing in your two script compared to the delta debug for the line. Just you keep the same script, you change only the name of your Verrou DD tools, and it will generate your search space, and it will say you that the problem is only in this line. You have to pay attention to one thing. This line means that you have localized the problem in the code between this line and the following one. So the code between 10,000 and 100,000 correspond to the 100,000 task rectangle. So you have to pay attention to the shift between the standard output and the computation. You have to pay attention to the bufferization. I mean, if your program write everything in the buffer and write in the standard output at the end of your program, you are not able to localize anything. But yeah, if you pay attention to that, you are able to do temporal localization without any effort. And it's even possible to modify the standard output thanks a user script to modify the definition of your task, and you can do really clever things with that. I have an example, but I think I speak too much, so I will be fast. Yeah, I won't give too much detail on this example. What you can remember is I'm able to, with this user script, I'm able to define in inner-outer iteration, I'm able to regroup inner and outer iteration. And this is really nice to be able to perform search for mixed precision. So to do mixed precision, to provide mixed precision configuration, I just have to replace the rounding mode equal random. I have to replace this part by a command to say I replace double operation by a float one, and at the end it will provide you a mixed configuration. So I won't give too much detail on it. Verrou is a really nice tool, but I'm maybe not completely fair. But as a user of Verrou, I'm still interested in the other tool of Interfloat. And the first one is Verificarlo. So it's really similar to Verrou, but it's based on LLVM. And so the computation time is better, especially with shared memory. And you have a better compatibility with the debugger. Yeah, the problem is you need to be able to compile your code with LLVM. And for me, sometimes it's just difficult to recompile the industrial application. So that's the main drawback, but it's a really nice tool. The second interesting tool is Pen. It's not yet production ready, but it will solve two problems of Verrou. The first one is Windows portability, and the second one is Valgrind is not able to do AVX 512. Maybe the most famous one, I think you have already heard a presentation of Cadna. So what is really nice with Cadna is you are able to get the accuracy for each variable. So that's really nice. The problem is the drawback is you need to modify your source code, and so this is difficult for industrial application. And the second good point is I can use it to perform comparison between the synchronous and asynchronous approach. That's nice. And the last one is it's no more stochastic arithmetic. It's based on affine arithmetics, and you can use it only with really small program, but you have a high level of confidence, and so that's really nice. So conclusion. So Verrou provides an easy floating point error estimation. That's really easy. It provides error localization with delta debug. This point is easy, and it provides also error localization with coverage. This point is more tricky. Verrou is used with industrial code, and you can use it because it's open source, it's available, and there is the GitHub address. I've still a lot of work to do. I need to improve the performance, and there is a lot of way to do that. I can improve the performance of instrumentation, I can improve the vectorization of the stochastic arithmetic. I think I can improve the data debug parallelism. So there is a lot of things to do for the performance. And the second point, I will need to improve the performance of localization. And the first thing I want to do is to add a backtrace search space. So, and the second one is to reduce the number of false positive of branch detection and cancellation detection. So, if you have questions, I'm ready for that.
Thank you very much, Bruno. Very nice talk. Thanks. Any questions to Bruno? Stephen, please go ahead.
Hi, Bruno. I'd like to thank you for this very interesting talk. Now, unfortunately, I had to miss the first few minutes of it, but I enjoyed the rest of it a lot, so thank you. I have a two-part question. So the first part question is, does this work on any kind of floating point representation? So besides single precision, double precision, could it work on, say, brane floats or tensor floats or anything in that sort of direction?
It doesn't work now. I think it will be possible with FP16 on ARM architecture.
Okay.
I think, but it's now I'm able. It can work only with x86 architecture and ARM.
Right. So this is a technical limitation, but not like a fundamental limitation of the approach, right?
I think so. With the tensor core, I'm not so I'm not sure because we don't know what is inside the tensor core. So it's difficult to introduce the white noise because we don't know what it is.
Okay. But I mean the tensor float thing, it's really just the same layout but with a different number of bits. And then the second part of my question is, would this sort of approach work with posits or unums, because they're a little bit more fundamentally different from the IEEE floating point numbers?
I don't know.
Okay, no, that's fine. That's fine.
I don't know because inside Valgrind, I'm quite sure it's no. Because I'm inside Valgrind, I'm using the error-free transformation.
Okay.
And I'm not sure it's worked with unit and posit.
Okay.
And in fact, inside Valgrind, this type are not defined in Valgrind, so I'm not able to get it.
Okay. Okay. Thank you very much.
I have just one question. On one of the slides, you showed the Valgrind call to Verrou, and there is an option libm equal instrumented. I kind of missed. So you're doing your own libm, or?
Yes. In fact, the problem of libm is if you modify the rounding mode inside the libm, you will get a lot of problem because they really use the guys of libm really use really tiny properties of the floating point, and you can if you use something like upward. You can get problem like seg fault. You can get a cosinus which is not between -1 and 1. So you have a lot of problem. And so the first way to solve the problem was to just ignore it. So the first way, the basic way is to say, I do not want to instrument the mathematical library. And that was during several years the way to do it. And now I'm able to, if your code is compiled with dynamically loaded mathematical library, I'm able to intercept each call to the mathematical library and to generate the one with the good rounding mode. And to do that, I need to be able to compute the error of the libm. And I'm doing something really bad for the specialist of mathematical library. I use the QuadMat library to be able to compute this error. I know there is few corner cases, but it's the only way I know to be able to do that. And so with that, I'm able for almost all the mathematical library. I'm able to produce to generate. I think I've 20 kind of random rounding, and I'm able to do that for all the mathematical library, except the complex one.
Thanks. Any more questions to Bruno?
I just wanted to say thanks for the talk. It was fascinating, and I appreciate you putting up with my questions in the middle of the talk.
Okay, I don't see any more questions to Bruno. So thank you very much for the presentation. This was very nice.
Thank you.
And yeah, so then I propose we close the meeting here, and please stay tuned on the mailing list for any new topics coming up in the Computer Accelerator forum. Okay, thanks everyone.
Thank
Bye-bye.
you.